All right, today we're going to talk about something that's, well, it's everywhere, but you probably never even see it. It's called signal processing. And really, it's the invisible science that translates our real physical world into the digital language that powers pretty much every device you use. No, I mean, really think about it for a second. When you talk into your phone, how does that physical sound wave, that actual vibration in the air, get turned into data that a computer can understand? How does it get sent across the planet and then magically turned back into sound for someone else to hear? Well, that's not magic. That's signal processing.
So here's the fundamental problem, right? We're dealing with two totally different worlds. Our world, the real world, is analog. It's smooth, it's continuous. Think of a flowing wave. But the world inside a computer, that's digital. It's all made of separate, distinct pieces, more like steps on a staircase. So the big question is, how on earth do you represent that smooth, beautiful wave using just a clunky set of stairs?
And that's where signal processing comes in. It's the magic toolbox that lets us bridge that gap. You can think of it as a whole set of rules and honestly some pretty clever mathematical tricks that we use to grab signals from the real world, clean them up, and then translate them into a language that machines can finally work with. Okay, so let's really get into it. We're going to follow a single signal, let's say the sound of your voice, on the very first part of its big adventure, getting captured from the real world and turned into the language of computers. So this whole conversion thing, it basically boils down to two key steps. First up is sampling. The best way to think about this is like making a little flipbook cartoon. You take a whole bunch of still pictures or snapshots, really fast. Sampling does the exact same thing to a sound wave. It takes thousands of these snapshots every single second. Then you have quantization. This is where each of those little snapshots gets assigned a number. It's kind of like using a paint by numbers kit, where you only have a certain number of colors to recreate a really detailed painting. But that begs a really important question, doesn't it? I mean, if you don't take your snapshots fast enough for that flipbook, the motion is going to look all jerky and just wrong. Well, it's the exact same for signals. So what is the magic number? How fast do you have to go to perfectly capture the original signal? Well, lucky for us, some brilliant people figured this out. It's a golden rule of engineering called a Nyquist-Shannon sampling theorem. And what it says is that your sampling rate, how many snapshots you take per second, has to be at least double the highest frequency or the highest pitch in the sound you're trying to capture. If you go any slower than that, you start losing information, things get distorted, and it all falls apart. It's the whole reason that CDs sample audio more than 44,000 times a second. It's to make sure they capture every sound a human can possibly hear. This theorem is basically a mathematical promise that our digital copy is going to be faithful to the real thing. Okay, so we've done it. Our signal is now just a long string of numbers. But for a computer to do anything useful with it, like say, get rid of some annoying background noise, it has to understand what's inside that string of numbers. It needs to see the signal's secret identity. You know, this is the way we hear things. When you listen to a piece of music, you hear it from beginning to end, moment by moment. That's called the time domain view. It tells you how loud the signal is at any specific instant. But a computer? It needs to see things totally differently. It needs to see all the ingredients of that sound all at once. All the deep bass notes, the vocals in the middle, the shimmery high cymbals. This is the frequency domain view. It's like getting a recipe that lists every single component that makes up the sound. So how do we make that switch? How do we go from one view to the other? Well, with an incredible piece of math called the Fourier transform. This thing is amazing. It basically acts like a prism for sound. It takes that complicated wave that's happening over time and it splits it into all of its individual frequencies, laying them all out perfectly for the computer to analyze. Okay, this is where it gets really cool. Because now that we can see all the ingredients in our signal, we can start messing with them. We can become digital sound engineers. We can precisely edit the signal to keep what we want and get rid of what we don't. Like that awful hum from an air conditioner that ruined your audio recording. And to do that, we have this amazing digital toolkit full of things called filters. Since we have that frequency recipe, we can use these filters with surgical precision. A low-pass filter lets us chop off all the high-frequency hiss. A high-pass filter can cut out a low, muddy rumble. And a band-stop filter, that can find and just erase a very specific annoying sound, like the buzz from fluorescent lights.
Now, I want you to just stop and think about this for a second. This whole process we just walked through, from analog to digital, from the time view to the frequency view, and then cleaning it all up. This isn't some abstract thing. It's happening billions, maybe trillions of times a second, all around you, right now. Think about your noise-canceling headphones. How do they work? It's pure signal processing. They're listening to the outside world, analyzing all of its frequencies, and then in real time creating a perfect mirror image anti-noise signal that cancels it all out. It's also how Spotify can shrink huge music files down so you can stream them instantly, and how your smart speaker can pick your voice out of a crowded, noisy room.
Or what about the photos on your phone? Ever wonder why they look so good even when you take them in a dark room? When you snap a picture, you're capturing a signal of light. And instantly, signal processing sharpens the edges, it brightens the shadows, and it gets rid of that grainy noise. The result is this beautiful, crisp image that then gets compressed into a tiny JPEG file. All thanks to these exact same techniques. And communications? Oh man, this is the absolute foundation of our modern world. Your Wi-Fi router and your phone are constantly doing these incredible signal processing gymnastics. They're pulling a clean, clear data signal out of an ocean of noisy, interfering radio waves. They filter everything out and correct errors on the fly just to make sure your video call doesn't drop. And it's not just about what we see and hear. It's about control, about safety. In a modern car, there are sensors sending signals about wheel speed and your steering angle thousands of times a second. Signal processing is watching those signals, and if it even thinks a skid is about to happen, it can apply the brakes to one specific wheel to keep you safe on the road, probably before you even realized you were in trouble. So, when you boil it all down, that's what this is all about. Signal processing is that essential, invisible translator. It is the fundamental bridge that allows our messy, physical, analog world to talk to the clean, powerful, and logical world of computers. So that kind of leaves us with a huge question, right? We've gotten really, really good at processing the signals of sound and light. So what's next? What's the next signal we're going to learn how to speak? Brainwaves? Gravitational fields? You have to wonder, the entire future of our technology might just depend on